Well, good afternoon. It's a pleasure to participate, even if at a distance, uh, in this wonderful conference, and also to celebrate the birthday of Victor Dodonov, who has been doing such wonderful work in physics in general and in Brazil here in particular. So, Zdarovia, Victor. And I hope this presentation is up to the standards of your wonderful conference. So let me start by saying that I have been working on the frontier between classical and quantum uh, mechanics for decades. And in this time, great progress has been done on the static properties of chaotic systems in classical mechanics, what the spectrum, the energy spectrum, uh, goes in quantum mechanics. And this is a successful story, but I think that in the meantime, one has left behind the question of the dynamics of what chaotic systems might be able to do. And so in the sequence of papers that can you see my mouse, by the way, or when I use it in the screen? Uh, well, I hope you can. So in these three papers last year, I started to work on the question of energy transitions, which include the situation where the eigenstates that one is looking at the transitions of are can be of chaotic systems as well as integrable systems, which are what usually come in the theory of semi-classical approximations. So let's look at some challenges. Uh, what remembers that actually when you do experiments, and of course the great thing about quantum mechanics in the past decades is that instead of merely describing what systems like atoms and molecules look like, it actually goes into the dynamics of experiments. But usually the initial states will be simple coherent states or integrable eigenstates, such as, for instance, Rydberg atoms. Uh, why is it that classically chaotic systems are never chosen as initial states in these experiments? Uh, Perhaps one difficulty is that experimental, if you think of a highly excited quantum state of a chaotic system, you have no selection rules for picking it out to start out. There will be a sea of states and you excite it up there and you don't know which state you have excited. Another problem is that really semi-classical approximations have never cracked the nut of what these states are really like. For instance, we know a lot about the spectrum, but the individual states, the characteristic features, and the relation to the underlying classical mechanics is not really worked out. Uh, but they are bona fide quantum states. So maybe sometime people will start playing around with them. So let's look at a specific type of excitation that you can do. Uh, I'm going to think now of situations where you have a state and you apply a unitary transformation, you know the full unitary operator, and you get new states. But instead of looking at an individual state, I will recall that what we do have good information for is the representations of assemblies of eigenstates. So let's say here's the density operator of a single eigenstate, you you get a narrow window, narrow classically, but a narrow window which contains several states, and you look at the spectral density operator, which is this mixed state combining all these individual states. And you take the Fourier, the Wigner transform of this uh, density operator, and you get a Wigner function. So if you look at the superposition, you get the spectral Wigner function, as I think was defined by Michael Berry. Now we get a unitary operator, and it evolves the pure states in this usual way. You sandwich them between the unitary operator, and so you get an evolved spectral Wigner function because each individual Wigner function has evolved coming from the operator. And so you put them all together and you have the transition Wigner function. And then if you ask for the probability density for a transition between two energies, E and E prime, you will have the probability will simply be the trace of the initial spectral Wigner function, spectral density operator, with the evolved spectral density operator, or in the Wigner-Weyl representation, this is just the integral of the pair of spectral Wigner functions. This is just definitions, right? Now let's look at what the smooth classical background to such a density is. When I say smooth, I mean that there are several parameters that you can bring in. For instance, I'm talking about here that you have the two energies, so these can change smoothly, and you have the parameter for the transition, which is this unitary operator, which I have supposed is an exponential of some Hamiltonian, but it can be anything. I'm supposing there is a continuous parameter for the unitary operators. Now, then, if you think classically, what the transition probability would be you have two, let's say, broadened microcanonical distributions, the original one and the driven one. Now you integrate them both together, and the classical probability would be the integral of both. Now, if you think of a microcanonical probability density, because after all, I have said that you have a narrow energy window classically. So if it's so narrow, you can approximate it as a delta function on the energy shell. You have just the integral over both energy shells. And this gives you the classical probability density. Obviously, this is smooth in terms of variations of the final energy, or the parameter of the transition. Now, if you think of what this integral is over, right? So it's the integral over two delta functions on two energy shells, right? Now, think of one energy shell is here, the other energy shell is here, and so it is an integral over the intersection of the two energy shells. So if you're in a 2n-dimensional phase space, then the energy shell is a 2n minus 1 dimensional sphere locally, and the intersection is a 2 to the n minus 1 dimensional sphere, right? And so you take an integral over this sphere, which I have called here xs, which is that section, and you it happens that you have two delta functions, so you get the Jacobian from one to the other will be just actually the inverse Poisson bracket integrated over the section. The section here, because I've just put down uh, n equals 1 here, which is the 1 degree of freedom, so two-dimensional phase space, and the intersection will be just a pair of points, which are these points. But for higher dimensional, you will have a sphere over which you integrate, and you then get eh, you just get this integral being the integral over the Poisson bracket. Of course, you have to go beyond that at times, and you then approximate semi-classically the spectral victor function, not just as an delta function, but as an Airy function with a width which is determined by local properties and Planck's constant. And so you will have a situation, for instance, where if you've taken the two shells far apart, there's no intersection, so energy transition density goes down to zero. When you put them together, you pass a caustic, and then you come into a smooth region where you vary according to the inverse Poisson bracket over the section. When there's no section, there's no classical term. Now I want to color this classical, smooth, rather boring transition density with semi-classical oscillations. And to do this, I will introduce closed compound orbits. Now, the thing is that coming back to this situation over here, I will now look at the situation where you see you've got the energy shell with E, and you've got, no, with E prime, and you've got the evolved driven energy shell with E, and they intersect. Now you can think that each of these shells makes a Poincare section on the other shell. So if I'm on the E shell, I can go from the intersection here back to the next intersection. Oops. And I will have trajectories going from one to the other, right? Now, sorry. Okay. Now, when so coming back to this graph, again, the lack of too many dimensions. What I here wrote down as being the energy shell itself, one can think of this as being one trajectory that goes here. And then I can get the Poincare map on the other energy section and come back here. And I can look at the fixed points of the pair of Poincare maps that I have made. And the fixed points then really denote a closed compound orbit, because there's an orbit which has come over here and an orbit which is in the other shell which closes into it. And there's the action of this closed compound orbit. So they are segments on the E shell and the E prime shell. And just as you see, when you have so you have a canonical map which goes and comes back, And you know that if you have a fixed point of a canonical map, if you if you continuously change a parameter, you get fixed points continuously coming from them, as long as you don't pass a bifurcation of the fixed point. So you will have uh, fixed points, and determined by the energy, the two energies, and each one of them has its time. Or likewise, you can think that you have families of compound trajectories given by t's, and you go from e to t, and you have the Jacobian determinant between them. So there are families of compound orbits in energy and uh, momentum. Now, now let's look at this in quantum mechanics. You have the, as we put it, before I introduce the unitary transformation for driving the transition, but let's look at the initial Hamiltonian and define the intrinsic evolution operator for uh, at the exponential of the initial Hamiltonian, right? Now, again, the final Hamiltonian, if you want to know how this has been transported, you just take the exponential of the transported Hamiltonian, and you have a compound evolution operator now, uh, which is the product of the two evolutions, just as we had a product of Poincare maps before. Now, the semi-classical trace of this compound operator is just exactly like in the uh, trace formulas for semi-classical situation. It is the exponential, that action that I put before, but now it's the time action, not the energy action. So you've got these extra terms over here, and you've got the but but the derivative of this action is just times, sorry, no, there should be no t here. It's just the e of t, because you take the derivative with respect to time here, and you just get e, and here you get e prime, right? Now, uh, let me see. And the stability matrix is just the stability of both trajectory segments put together, right? Now, you see that you immediately get the sign that you might get caustics here when the the full stability matrix comes to the identity. That's the situation that I talked about in the classical term, where the two energy surfaces are tangent. Now, this is like the periodic orbit case, but there are two differences. One, there's no, since you've got two different trajectory segments, there's no direction which is trivial as in a periodic orbit. The other one is that there's no minimum uh, time for a compound orbit, because if you've got uh, two sections which merely just have just passed the caustic, then they are very small uh, trajectories that might be coming in there, unlike periodic orbits where there's always a minimum size of the orbit. Now let me look at the full uh, compound trace formula. So I start with recalling that the spectral Wigner function, which I defined before as being a bunch of individual Wigner functions, can be looked at as the Fourier transform of this uh, intrinsic evolution operator in the Wigner-Weyl representation gives that spectral Wigner function which I defined before. Then the exact formula for the transition density becomes an integral over the two spectral Wigner functions, which have been coming here as before, not the delta functions that we had classically, but now full quantum mechanical uh, spectral Wigner functions. And then finally, switching the integrations here, uh, you get the double Fourier transform of this integral over the pair of Weyl. These are the things for which we have the semi-classical formula. And then we recall that in the Wigner-Weyl representation, the trace of the what we had of the two operators, so this is the compound operator, is just the integral of the two Wigner functions, which is what we have over here. So uh, we have a double Fourier transform of the trace formula of the compound evolution operator. So this is the trace of the compound evolution operator. And here are just two Fourier transforms of this trace give you the desired uh, transition density. And we recall that we know semi-classically what this trace looks like. So you have those oscillations. Here are the actions of the oscillatory terms. Since the integral you see goes over positive and negative times, you get for each term there is the complex conjugate, so you have cosine instead of complex exponential, and so you have the when you take the integral by stationary phase, there will come out the Jacobian. The stationary points will be just the compound uh, the compound trajectories, and this determinant over here, this Jacobian comes in from the stationary phase condition. And here is the amplitude that we had of the compound trajectory. So you get sum over all trajectory segments in the E shell and the driven E prime shell, traveling forward and backward in time, which combine to form uh, com- to form closed compound orbits. The long segments will be dampened with you see the long trajectory segments get this damping over here. This comes from the energy window that we have put in. The smaller the energy window, the longer the time, the more compound orbits will come in. And you and if you've got very small, one trajectory is very small, then you just get the periodic orbit itself. Right? Now, so I want to sort of give a sketch here of the relation of what I have presented to the Gutzwiller-Tritz formula. One way to look at the Gutzwiller-Tritz formula is get the trace of the evolution operator. It's not how it's usually done, but I think this is a nice way of doing it. Then take its Fourier transform in time, and you get the smooth density of states. Right? When you look at the classical, semi-classical evaluation, you get all the periodic orbits in the energy shell with repetitions. and this gives you the Kutzwiller trace formula. Now here we want to look not at the smooth density of states, we want to look at the smooth density of energy transitions. And you start from the trace of the compound evolution operator, so which has got the original and the final evolution operators. You take the double Fourier transform and you get the smooth density of energy transitions. The semi-classical evaluation, instead of relying on periodic orbits in a single energy shell, rely on closed compound orbits joining the energy shell with the driven E prime shell, with no repetitions. You see, here you've just got pairs of orbits here and here, and what comes back is not like in a periodic orbit, it's actually periodic, so it keeps repeating itself. Here it doesn't repeat itself. You have to look at all the possibilities, but you have all the possibilities for all the possible uh, returns of the Poincaré map to the Poincaré section. So iterations of each of the Poincaré maps all come in into this sum. Right? So let me uh, see how I'm doing. Well, I think I've got plenty of time, so let's go into the discussion. Uh, you get a universal imprint of energy transition density oscillations onto a smooth classical background produced by arbitrary unitary evolution. So I have not said in any way what kind of motion there is in the energy shell. It might be integrable, it might be mixed, it may be chaotic, but I'm talking about finite time evolutions. And for finite times, you've got the Poincaré maps, and you get the trace of you get the fixed points of these Poincaré maps, give you the trajectories which you need, irrespective, right, of the type of whether the unitary operator was obtained from a single Hamiltonian, a time varying Hamiltonian, or anything, and also whether the initial system was chaotic or integrable. I have in this presentation hidden all the Wigner-Weil calculations that I did to derive the results. The important thing is that since it should describe experiments, it must be independent of any representation used. So conceivably, one could have used other methods to arrive there. But the point is that the phase and the amplitude of the contributions of the closed compound orbits are indeed independent of the Wigner-Weil representation that I use to arrive there. Now, in practice, all results refer to fast processes. Why? Because I have supposed that I know what the unitary operator is that has driven the process. Whereas uh, usually, you see, you would need to solve the Schrödinger equation to know what this operator is in the first place. But the structure that I have presented does not depend on what it is. So this structure, I think we can rely on, and the details of what the actual calculation will be different. But you just as a in the static case, you have a smooth Weyl density and you add oscillations. Here, for the transition, you have a smooth classical density and you also add oscillations in terms of classical orbits. Even if you cannot quite generally know, unless, of course, you've got a kick. The kick gives you immediately the U, and you don't have to do it. So you can, for kicks, you can try to see how these predictions work out. Now, you see, if you do not know this over here, classically, of course, we have, you can, if you know the transformation in time, you can integrate orbits and you can get there from the initial Hamiltonian to the final Hamiltonian. But I have asked for more. If you look at the classical superposition, you can calculate a superposition of two energy shells by putting lots of orbits in and doing a Monte Carlo integration and finding out a good approximation. But I have asked for the orbits of the driven shell. Now, that requires that you know differentially the Hamiltonian to be able to calculate the trajectory. And that's uh, hard unless you have a kick. But uh, beyond this last paper, which I have used, of the three papers that I cited before, I have here used mostly the last one, which was actually a paper which Andrei Klimov invited me to participate in a special issue that he was organizing. But now I have almost ready a new development, you see, which is that I can expand the present treatment to arbitrary time-dependent Hamiltonians, not just kicks, right? So, for instance, my driving Hamiltonian might be the initial Hamiltonian plus some parameter with some time dependence. And then I have the trajectories of the driving Hamiltonian. So then you see, I can use the following fact that the what I have done before is that I have the final the initial Hamiltonian with the energy shell, its initial energy shell, and this would be the driven energy shell. But there is a Poincaré theorem which relates the action along this along the trajectory which has been driven to you can obtain it from looking at the driving trajectory. Then you go back to the initial. You see, this is the image of this over here. So you go back here, go along the black curve, not the dashed curve, and back here, and you say that on this quadrangle, the action is zero. So you can relate this action to this, and so you can get a instead of the simple compound orbits with two components which I have put in here, you get the full general theory by combining four trajectory segments, and all of them are the Hamiltonian ab initio. So you do not have anywhere the trajectory of a Hamiltonian which you do not know how to calculate. Here, the red trajectories are given by the driving Hamiltonian. The black trajectories are given by the initial Hamiltonian. So you know all trajectories, and you've got now two Poincaré sections which you have to join by the red trajectories. So this is a bit more complicated, but I'm saying though that with this addition, I think that now one can look at real situations like, for instance, putting an electromagnetic field and seeing how it oscillates and all these transitions that you know, but in a situation which is completely non-perturbative. There's uh, no assumption that this parameter over here is small. It can be as large as you like because you can always integrate the trajectories that you need for this kind of semi-classical theory. So I think that I can stop there, and I think there should be, I think, time for some questions. Thank you.
Thank you.